Okay, we're recording. So this is lecture 2 for MRI, and the topics we're going to cover today is we're going to review a little bit of Fourier transform, case-based review. For those of you who came to the supplementary session, this will be a little bit of review for you. Then we're going to talk about how we use the gradients to do encoding. We're going to go over the MRI signal equation, and then we're going to talk about case phase trajectories and pulse sequences. So this is really a lecture where we take a first stab at understanding how we use MRI to actually make images of objects. So just a little bit review of last time, and then we'll also talk a little bit about the pre-lecture quiz. So there were 4 main steps we talked about. The first was we used the main magnet is for polarization, and that's to create some magnetization that we can work with. The second phase is excitation, which we use to take that magnetization and excite it away from its equilibrium position, and then it's going to be excited away, and then it's going to process around the main field. The third main component is the gradient coils, which we'll spend a lot of time talking about today. And that does what's called encoding, which was one of the answers to the quiz, which is gradients are primarily used for spatial encoding. And we'll talk a little bit more. We mentioned that last time. Today, we'll go into more depth on what that actually means. We'll also then talk about how the RF coil is used once again in receive mode to integrate the signal. And so the idea is the RF coil not only sends energy into the object, but it also receives the signal from the entire object, or at least part of the object. And that receiving of all those signals from all the spins, we can consider an integration process. So what I'd like to do now is we're just going to go over some of the questions in the quiz that was just due a few minutes ago. And there were some questions that most people did very well on, and there were a few questions that, especially question 6, that we definitely need to go over. All right. So let's just sort of review a little bit where we are. So we imagine we have some M0 equilibrium magnetization, okay? And that's typically in line with the B0 field. So the first thing we can think about is we typically have these coordinates Z, X, and Y, okay? And by definition, we imagine the M0 is aligned with the coordinate system with the Z coordinate. And so what we're going to do is one of the questions was what happens if you have a theta equal 30 degrees. Let me see how the question is phrased. And the RF pulse, so remember there's a B1 pulse. So we're applying a B1 pulse along the x-axis, okay? And remember, precession always in MRI follows the left-hand rule. And so if you want to know which way things are going to process, you point your thumb in the direction of the main field, or whatever the B1 field you care about is, or the B field you care about is, and then the direction of your fingers tells you which way it's going to process. So for example, around the main B0 field, there will be this precession in this direction, okay? So if we have the B1 is pointing along the x-axis, that means there's going to be the magnetization is going to process in this direction. So it's going to go from the x. So if this is the x direction and this is the z, it's going to do a clock. It's going to sort of do this left-handed rotation around here, such that the magnetization will process in this way. Okay. So it's basically going to tip the magnetization a bit onto the y-axis, and there'll still be some on the z-axis. So at the end, if I have 30-degree tip angle, okay, and this magnitude is 1, then we know on this axis it's just sine theta, so that's going to be 1/2. So my component is 1/2, and then along this axis we have cosine theta. Okay, so along the z-axis it's cosine of 30, and along the y-axis it is sine of 30, so 1/2. So that's an example of for that problem. The correct answer would have been my equals 0.5, mz equals 0.87. Okay, so about 70% of the people got that. Let me just see if, just update and see if anyone else has done the quiz in the meantime. Okay. So then we tip the magnetization away from the axis, right? And then it can spin around the axis. And so we said that the spins are going to precess the mxy component is going to sort of be proportional to e to the minus j omega naught t. So that's going to be the precession of the transverse magnetization. And first of all, let's just review omega naught equals gamma over b naught. Similarly, in Hertz, it's gamma over 2 pi b naught. Okay. And so for hydrogen and proton, we know that gamma over 2 pi is equal to 42.57 or thereabouts megahertz per Tesla, or 42.57 hertz per Gauss. All right, and if you have trouble remembering it, those of you familiar with the Hitchhiker's Guide to the Galaxy know that the answer to the universe is 42, and so you can it's sort of funny that the gyromagnetic ratio of hydrogen and proton is also about 42. And so we know that in one of the questions it said the Earth's magnetic field, and so you know that from the class, and also maybe from some of the measurements if you've already started homework, the Earth's magnetic field is around 0.5 Gauss. Okay, so we know that half of this is going to be around about 2100 hertz. Okay, so 2000 hertz would have been the correct answer, and I think most people got that. Or at least only 56% of the people. Oh wait, let's see which one is that. Yeah, so 84% of you got that right. Then the other thing we have to talk about is, as the magnetization is precessing around, it's going to relax as well. And so we said that there's going to be a relaxation of m sub z. That's going to follow e to the minus t over t1. And then there's going to be this decay of mxy that is sort of proportional e to the minus t over t2. Okay. So therefore, one of the questions asks you about T1, T2, and so note that T1 relates to M sub Z, and T2 relates to MX and MY. All right. So that covers most of the problems. The one problem that most people actually got wrong, so let's talk about this, was the last one, where you're given that the F naught is 1000 hertz. Okay. And so you assume that, for example, at t equals 0, you're at a 0 phase. So this is at t equals 0. Okay. And you're asked to, at t equals 250 microseconds, where's the magnetization going to be? And we're going to see some other problems very similar to this as we go through the lecture. So one thing is, for 1000 hertz, that means it takes 1 over 1000 hertz to get one cycle, right? So this is equal to 1 times 10 to the 3 hertz. Okay, so that means 1 period is equal to 1 times 10 to the minus 3 seconds, or 1 millisecond. Okay, so in 250 microseconds, we will have gone a quarter of a cycle. Okay, so that means a quarter of a cycle is 90 degrees. So then you know it's going to be either plus 90 or minus 90. And so then the question is, which way does the magnetization go? Does it go plus 90 degrees or minus 90 degrees in that 250 microseconds? And so there we go back to here, which we derived last time, what we talked about last time, is the magnetization has this e to the minus j omega naught t dependence. And so as time increases, the angle becomes more negative with that precession. Okay, now this is assuming we haven't applied any additional gradient fields. But even if we do, the net field will always be this if you're in the laboratory frame, it'll always be this negative precession. Now, if you're in the rotating frame, it can go plus or minus. But in this case, you're only given the resonance around the main field. And so what happens is that t equals 250 microseconds will have gone this way, so minus 90 degrees. All right, so are there any questions on that before we move on to the main lecture? So I will say that these are called pre-lecture quizzes, but it might be a good idea to actually leave some time, don't do them right before the lecture. They're really meant to help you review the previous lecture and maybe additional information. And so make sure you give yourself enough time to do these quizzes. They're meant to help you consolidate your learning. Okay. So I don't see any questions. So let's move on to the main lecture then. So what we're talking about today is MRI gradients.
And hey, my 2 quick questions. Sorry, my microphone wasn't working.
Okay. You want to go back?
So yeah. Just the homework, there's an async function, sync spelled S-I-N-C. Is that different from the sync function?
Oh, there's a misspelling? So it's S-I-N-C like that? How is it spelled?
It's A-S-I-N-C.
Oh, it's it's like A is some amplitude times a sync. So you're
okay, gotcha.
A. Yeah. So sorry about that. Yeah, so basically A is this unknown amplitude. I think you have to solve for that.
Okay, and then a quick other question about the left-hand rule versus the right-hand rule is I've always used the right-hand rule, but is that because we were using conventional current, pretended like they were positive charge flows, but now it's actually positive flow, so we use left to be consistent with the other one?
That's basically due to the fact that the geometric ratio has this it basically is just how things work in terms of which way it just happens to be that for hydrogen proton, it follows the left-hand rule around the magnetic field.
Oh, I see. Right, because each has its own direction of spin, right? Okay.
Yeah. Yeah, that's right. So you can have negative geometric ratios, which goes the other way.
Okay, thank you.
So it's just nature has made it that way. Okay, let's move on then, if there's no other questions. So yeah, today we're going to talk about the MRI gradients. So this is just to remind you that we're going to have an X gradient, a Y gradient, and a Z gradient. And this is what a gradient coil looks like. Here you're seeing basically the X and Y gradient coil patterns here. Okay. So the important concept is we know that spins always they precess at the Larmor frequency, which is proportional to the main field. Okay. So if we just have the constant static field, then they will precess according to gamma B naught. So we have omega equals gamma B naught. And gradient coils then are used to add a spatial variation to B sub Z, such that now we could have something that it would be omega naught plus some delta omega naught. Okay, so the idea is we're going to make spins at different locations precess at different frequencies. So here's a picture. So remember, the center is what we call the isocenter. And so then spins there will precess at gamma times B naught. In this case, we've applied a gradient field in the x direction, so gxx, where gx here is positive. And so the field gets stronger as we go along this direction. And so the spin over here would precess faster, so that gamma B naught plus gamma gxx. And spins here would precess more slowly, so gamma B naught minus gamma gxx. Okay. So this is a movie I captured from the RAD 229 video lecture series from Stanford. And so this shows let's say this is the x direction. So this shows, in the presence of a gradient. Well, let's actually stop this one. Does someone have a question there? Okay. Okay, I think when I was recording this, my daughter was in the room, so that's what that is from. Okay. Okay. So I think that what it's showing is, okay. So what you're seeing here is on this one, this is the spins are processing here. They're processing in more quickly than these spins here. So these are at the isocenter, so they're not don't have any additional spin. And these spins here are processing more slowly. And so everything here is in the rotating frame. And so you're seeing that you can get spins processed in the rotating frame either faster than the spins at isocenter or more slowly than spins in the isocenter. Okay. And if you apply gradients in both the x and y direction, then you can get spins processing sort of in an off-diagonal direction. Okay. So let's do a problem here. So this is actually problem 12.1 from the book, which we're not going to assign to you, but we're going to work through it together. So here's the problem. So you have a B field that varies with B sub z equals 1 plus 0.5 z. Okay. And so this one means it would be 1 Tesla. So this is in Teslas. Okay. And we're saying the magnetization vector processes around the z-axis. And suppose at time t equals 0, all the magnetizations have the same phase. And we want to consider two spins, one at z equals 0 and one at z equals 1 centimeter. Okay. And you're asked to figure out at what time will the magnetization vector at z equals 1 and z equals 1 and z equals 0 have the same phase again. So the one at z equals 0, okay, that's at isocenter. So that's just going to, since it in the rotating frame of reference, that doesn't experience any additional field. It's just going to stay at theta equals 0. Because that's an important concept. In the laboratory frame, it would be processing at omega naught. But now we're going to assume everything is in the rotating frame, and so anything at isocenter, that spin just stays where it's at. And so this spin here is going to spin like that. All right. And so we want to sort of figure out how much time it takes for that spin to come around 360 degrees. And it's also asking what will the phases be at 0.25 centimeters, 0.5 centimeters, and 0.75 centimeters, given the time you've calculated for that spin at 1 centimeter to go all the way around the circle. So let's work this problem together. So we know that the difference in the two spins at one, so the delta B is 0.5 z. Okay, so that's 0.5. And then we've got 1 centimeter of difference here, okay? So there's 0.5 Tesla of difference, which is quite a bit of difference between those two spins. Right? So the next thing we have to calculate is the difference in precession frequency. So that's delta F times gamma over 2 pi times the difference in those two spins, okay? That's the change in the field between the two spins. And so we can take 42.57 megahertz per Tesla times half a Tesla, and we get 21.285 megahertz, right? And so we know that that's delta F is the frequency, so that's the cycles per second. So we know that one cycle happens, the period is just 1 over delta F. So one cycle occurs in 0.047 microseconds, all right? So that means that it takes that much time for the spin to go around and make one full cycle, okay? So we know that between 0 and 1 centimeters, if we wait that much time, this spin will have gone all the way around, okay? And then we know, sort of using that logic, if we have a spin at 0.5 centimeters, because it's only got half the field strength difference, it's going to only process half the way. So it's only going to go pi over 2. Okay, so in this case, minus pi, because it's a clockwise rotation. All right, and that can be obtained here, where in this case, the delta F is only 1/2 of the delta F used here. And so it's only going to go halfway. And similarly for all these other ones, this is only going to experience 1/4 of the field. So it's only going to go 1/4 of the way. And this one here would go for 270 degrees around. Okay, so basically, the farther the spins are away from isocenter, they're experiencing more of a field difference, and so they're going to precess faster and therefore acquire more phase in a given amount of time. Okay, and so that's basically what we refer to as the rotating frame of reference. And essentially, if we imagine the spins precessing at the Larmor frequency, then they might be precessing around here, like that. And but at isocenter, we imagine that that spin will just be steady like that. Okay, so that's once again saying at z equals 0, the spin is just always going to be any spin at isocenter for the purpose of this class is always just going to be staying at theta equals 0. Okay. So if we were doing this in person, we'd have some of you get up and we'd do sort of an in-class exercise using people to mimic what spins are. But since it's on Zoom, we sort of have to make do. So this is what the experiment would look like. So imagine each person here represents a spin. And so these are, for example, 5 spins in different locations. And at time equals 0, they're all aligned, okay? So they all have theta of 0 degrees, right? And then we're also going to consider that we're going to, and this is isocenter, this spins at isocenter, and we're going to also imagine we're going to put a magnetic field gradient here of the form gx, x, all right? Such that this spin here will spin faster so that every time step, it's going to go minus, let's see what I have, minus 180 degrees. This spin is going to go minus 90 degrees at every time step. This spin is going to go plus 90 degrees because it's lagging behind the spin at the isocenter. And this spin is going to go plus 180 degrees at every time step. Okay. So basically, the farther the spin is away from the isocenter, the more phase it's going to, for every time step, it's going to acquire more of a phase increment. So let's go one time step. Let's see here. So you can sort of see here, this phase stays here. This guy has turned 90 degrees. So if we look from on top, it's here. And this one is there. And this spin is pointing in this direction. And if we're looking from on top of the person, this spin would be facing away from us. Okay. So you can sort of see that we've already, by just going one time step, so this is sort of one time step, we've actually created this spatial pattern of the spins. And so, for example, one period here of that spatial pattern goes from here to here. Okay, so one period, let's say the spacing is 1. So here we would say the spatial period is 4. Okay, so the period is 4. And that could correspond to kx, for example, equal to 1/4. Okay, so we would say that that sort of orientation of spins has a spatial period of 1/4. We go one more time step here, and now the spins are pointing like this. Okay, and so you see now the spatial period is gone down to 2. Okay, and so this would be a kx of 1/2. Right. You can go one more period, and now look at this spin at the isocenter is always staying the same, but now we have this guy pointing away from us. This one's pointing opposite to that one, this pointing towards us, and this is pointing away from the spin at isocenter. So once again, we have a period of 4. Okay, but notice that this is now we would call this probably kx equals minus 1/4 because the orientation is different. The spin orientation is such that it's sort of the same period. These two have the same period, and whether the sign is correct or not, it's actually, this is probably plus 1/4, and this is minus 1/4. Yeah. or no, I think the opposite way around by orientation. Okay. But in any case, so that's an example of positive and negative frequency. So you have the same spatial period. It's just that the way the spins are doing that, there's a sort of a different handedness to the spin rotation. And then finally, at the end, in this case, after we've taken the last time step, all the spins are pointing back in the same location. And so we would call that kx equals 0. Okay. So kx equals 0 means there's no variation in the orientation of the spins, and therefore we're at the center of k-space. Okay, so this is just sort of showing it from a top view. Basically, once again, we have, this spatial orientate. This is the period of 4. Now we have a period of 2. So this is kx equals like minus 1/4. Kx equals a half, or we can call it minus a half. And then this is kx equals 1/4. And this is kx equals 0. And this is kx equals 0. All right, so the basic idea is that if we just apply this gradient and let it run, then spins at different orientation, at different spatial locations experience different frequencies, and therefore over a given amount of time, they're going to acquire different phase. By controlling that distribution of phases, we can get different parts in Fourier space. Right, so these complex phasors that we look at, e to the j 2 pi kx x in our Fourier transform, these are actually implemented for us by getting the spins to point in different directions, depending on where they are in space. Okay, can you clarify why something would spin plus 180 versus minus 180? I'm a little fuzzy there. Okay, so that's a great question. So from the point of view of whether something's 180 or minus 180, we can't really tell. But we can sort of look at the path it got there. So for a spin that's spinning faster than isocenter, so because we're talking about clockwise rotation, we know it went this way. Okay, so it went 180 degrees that way. A spin that's going faster, that's slower than the one at isocenter, goes this way because it's sort of lagging behind. Because things that are going faster in the clockwise rotation. So if something's going slower, it's lagging behind, and so this would be minus 180 degrees, and this would be plus 180 degrees. Okay. So, but when we look at the spin at any given time, we don't actually know how it got there, and that can lead to an issue that we're going to talk about aliasing in a future talk. And so, at any given point in time, if you just look at the spin orientations at any given point in time, you don't really know how it got there unless you're given more information. But so the idea is spins can get to the same location by either spinning faster or spinning slower. Right? Okay, so now we're going to sort of review, try to put this into more mathematical terms so we can sort of build up what we're doing with the MRI process. So recall that for a 1D Fourier transform, okay, so it spins so fast that it's backwards. Here's the way to think about it. If you are, let's say you had people, let me just drop, let's see where we have some space. Let's say we had people running around a circular track, right? So the race was around, you're running around a track, okay? So, and one person is sort of in the middle of the pack, and one person's faster and one person's slower, okay? So for example, let's say after some point in time, the person in the middle of the pack is at this phase, all right? The person at the front, let's say the fast person is here, so he's gone faster, and the person in the back of the pack is lagging behind. So the phase we're talking about, since we're referencing everything to this one, who's at the isocenter, then this is the phase we're talking about. So this would be the minus, let's say, theta, and this would be the plus theta. Okay, so the phase is sort of where you are in reference to that person in the middle at z equals 0. They're all spinning really fast. They're all spinning very close to 42 million times per second. So it's just that difference in how fast they're spinning they're all spinning clockwise very quickly. And so it's just that minor difference in how they're spinning with reference to the spin at the center of the magnet that we care about in the rotating frame. All right, does that help? All right, good. So this is the definition of the 1D Fourier transform. And remember, so we have some object g of x times e to the minus j2 pi kxx. And so we know we need a phase term of the form theta minus 2 pi kxx. Okay. And so remember that the way we look at it is, so basically we want some phasors that have theta that follows where we are, depending on if we have some sort of kx, it will have a phase that depends on x according to this formula. Okay, so let's take an example. For all these, we're going to have kx equals 1. Okay, what does kx equals 1 mean? Well, it means that there's one cycle, let's say, per centimeter, if we're in centimeters. So that means if there's one cycle per centimeters, that means that one period is 1 centimeter. So it can take 1 centimeter for the spins to get back to sort of have that spatial pattern repeat. So at x equals 0, 2 pi kxx is just equal to 0. So we have theta equal to 0. All right, so that would be something at 0, kx equals 0. At x equals 1/4, we're a quarter of the period, right? So we would expect the phase to be a quarter of a cycle, which is 90 degrees or pi over 2. And since it's negative, it's negative pi over 2. Okay, because we've said that the phase is minus, has this minus term in front of it. Here we have x equals 1/2. And so that's half a period. And so we'd expect the phase to be pi or 180 degrees. And in this case, we can just say theta equals pi because pi and minus pi are the same. And here we're at x equals 3/4. So we've gone 270 degrees around. And so here we can say that the phase is 3 pi over 4, but that's also the same as theta of plus pi over 2. Okay, so by 270 degrees this way is the same as going 90 degrees the other way. So this is then another way of looking at that. So here what we're looking at is phase patterns at different, at different frequencies. So at kx equal to 0, anytime you see kx equals 0, ky equals 0, that's basically saying you're at the center of k space. And so that means there's no spatial variation. So if you look at the orientation of the spins there, you see that they all have theta equal to 0. It doesn't matter where they are in space. So the kx equals 0 just means wherever you are, the spins should always be pointing in the same direction. Now let's take kx equals 1/8 delta x. So that means the period, let's call the period, would be 8 delta x. Okay, it's just 1 over the spatial frequency. And so that means that here we've shown this distance here is 4 delta x, right? So over the span of that, we basically, if the period of that is 8 delta x, we would expect half a period of variation across for this frequency for this span. And so you notice that indeed we have that. This is pointing up and this is pointing down. So that represents half a period of variation. Here we have kx equals 2/8 delta x. So here the period would be 4 delta x. So that means in 4 delta x, we should repeat our pattern. And you notice we do. We sort of have this is pointing this direction, this is pointing that direction. So in 4 delta x, we've got the spin to repeat the pattern. And so that's how you can sort of start thinking about relating different places in k sub x or k sub y to the orientation of the spins. All right, so notice here we have this gradient gx of x, and things here are going faster and things here are going slower. So as we take as we go from 1 kx to another ky, you notice that it's this phase. These are going this direction, so they're gaining speed as compared to this one, where these are lagging behind. Okay, and then this one's going even faster, so it's gained a little more, and this is lagged behind even more. Okay. As we let time go on and the race keeps going on, and the person in the lead is still running faster, they will have gained even more of a lead compared to this guy, and this really fast spin has got even further ahead, whereas this has lagged behind further, and this has lagged behind the most. Okay. So yeah, given this, I think that the signs for the kx and ky that we did in the initial one should probably be reversed, but we can fix that in a later presentation. Okay, so now we're going to move ahead to reviewing a little bit about what K-space looks like. And so some of you, this will be hopefully a review for most of you, but it's good to just sort of make sure everyone's on the same page. So we've mostly talked about things in 1D, but obviously for images, we need to talk about 2D. So just recall that the definition of the Fourier transform, we've got a double integral. We're taking the object and multiplying it by this 2D sort of complex exponential. And then the good thing is we can also do the inverse Fourier transform. And from the Fourier transform, we can get back our object. So we talk about image space, where we might define things as a function of x and y. And then we have K-space, where this is the Fourier transform of that object. And here, the units are kx and ky. And so we just want to spend a few minutes reviewing how do you look at Fourier space and what are different parts in the kx, ky, or K space. So we typically talk about this as K space. What do they mean? So let's just write out this complex exponential using Euler's theorem. We can write this as cosine of this argument plus j sine of that argument. And so for different parts in K space, there's going to be different spatial patterns associated with it. So we know that, let's say this is K, let's say we're in Kx, Ky space, and here we're at some point along the Kx axis. So this might correspond to this spatial pattern, okay? So for here, Ky is equal to 0, right? Because we're along the Kx axis. So we know there's no sine component. And so this is just going to be something that varies as cosine 2 pi kx of x, right? So it's only going to have a variation along the x direction. And it's going to have variation such that the spacing of the peaks of that variation is 1 over kx. Okay, so the spatial frequency is kx. You know the spatial period is 1 over kx. Then we come out to some point in K space like here, where we at some point in ky, and so that would be here. Okay, so this corresponds to this spatial pattern. So now kx is equal to 0, right? Because we're along the ky axis. And so therefore, the dependence on ky goes away. So we'll have either a sine or cosine, depending on the phase dependence on y. So there's only variation in the y direction, right? And here, if we're at, let's say here, we're at some point in K space, so Kx, Ky, there's both Kx and Ky, then we're going to have a diagonal stripe, okay, because there's variation in both the X direction and in the Y direction. And it turns out here, the spacing between the peaks is given by this formula here. So this is just showing that if you do have something in diagonal direction, this, oh, I think I'm missing something. This spacing here, you can show is 1 over kx squared plus ky squared. All right. And then if you look at the supplementary session 2 notes, I think there's more detail on that. But in terms of how to think about K-space, probably the best rule of thumb is as follows. Let's say you're given some arbitrary place in K-space. Okay, so let's say I'm out here in K-space. What you can think about doing, if you want to think about the spatial pattern that corresponds to that place in K-space, is just draw a vector from that point in K-space out to here. Okay, and then if you draw components that are perpendicular to that vector, that will tell you the spatial pattern that's associated with that part of K-space. And if this is some angle theta, okay, so you notice it has that, it's basically telling you sort of in which direction are those spatial patterns going to be perpendicular to. And then you also know from Pythagorean theorem that anywhere you are in K-space, the magnitude of that vector is just square root of kx squared plus ky squared by the Pythagorean theorem. So 1 over that gives you your spatial period. Right? So those are some sort of useful sort of rules of thumb to keep in mind. Another really important part is the center of K-space, which actually I think you can use this fact also in your homework, which is basically if I look at g at 0, then that is just the integral of my function in 1D, or if I look at g0, 0, then that is going to be the 2D integral of my function. So the center of K-space essentially is sort of like the mean value of your functions, the area under the curve. Okay, and so since most objects, have a mean area under the curve of their object, then typically when you look at K-space, if we're looking at say kx, ky, typically the center of K-space is very big, and then things fall off. Okay, as you move away, because there's most of the energy of the signal is near the center of K-space for most of the objects that we'll be looking at, not all of them. Okay, so let's quickly go through this example. So of how moving through K-space. So this green dot here shows you one point in K-space, and it might have this sort of spatial pattern. As I move out farther in K-space, you notice the farther I move out along the x-axis, then that spatial period gets smaller because I'm going to a higher frequency. If I look at some place along the ky axis, so this is kx and ky, then you notice now we have spatial frequencies moving that direction. And as I move farther out in K-space, I get even finer spatial frequencies. So notice that this rule of thumb, if I took an arrow from the origin to where I'm in K-space and I drew perpendiculars to that, then that gives me these spatial patterns. And similarly, if I have something here, I could draw an arrow like this, and the perpendiculars to that would give me this spatial pattern. All right. So different parts in K-space, you can think of them as corresponding to different sort of spatial patterns of these sines and cosines. This is a movie just showing sort of as we get more and more of K-space, how the image is affected. So you can sort of see that the center of K-space covers sort of the low the overall shape of the image, okay? But it's very blurry. But it's capturing the overall, is this a ball? Is this a person? So from the center of K-space, you can sort of get a feel like, okay, well, it's something there, but you can't really tell what it is. And so it's only as you acquire more and more of K-space that you start filling in all the details, right? So the center of K-space is really giving you the overall sort of shape and the mean level. And then there's these outer parts in K-space here that are giving you the fine details. So let's quickly go through some examples of that. So here I've got, this is the Fourier transform of my object. If I cut out all these parts, so I've just zeroed these out, so it's set to 0. Okay. So what I'm doing is I'm getting rid of information that has sort of correspond to ridges like that. So if we zoom in on this image here, you notice these edges here are pretty sharp in this image. And then here, they're fairly blurry, okay? Since I've gotten rid of that detail, right? So that's what happens when I get rid of that part of K-space. There's more examples in the supplementary session. Here, what I've done is I've just added on a k-space component here. And so I can imagine drawing something here, and I know I'm adding on lines like that. And so this image now will have these horizontal stripes in it. Here, I've added some energy out here in k-space. So if I add on that, this is going to add diagonal stripes to my k-space. These are called corduroy artifacts. You do see these once in a while in MRI. So sometimes there might be some interference, either coming from external source or even just sometimes metal hitting itself with vibrations. These can cause a little bit of energy to get into the coils. And that energy can end up any place in k-space. And depending on where it ends up, that's going to give you these stripes. Okay, so these are called corduroy or zebra artifacts in MRI. Okay, so we've mostly focused on, just to give an overview of what k-space looks like, we mostly focus on these spatial patterns. But for MRI, we really want to start thinking about things in terms of the phases, right? And so for every sort of one of these sort of image patterns that we have, there's actually a corresponding orientation of the spins, okay? And in fact, this is much more, this is basically essentially, a physical invitation of this complex phasor in 2D. So here you notice that if I look at this, it does have these sort of diagonal kind of patterns to this in terms of the phase orientation. Okay. So let's look at some initial phase orientation. So for example, if we're at the center of k-space, kx equals 0, ky equals 0, then that means that there's no variation in any direction. And so all the spins are pointing in the same direction. They all have 0 phase. If we go to some place kx equals 0, but ky is not equal 0, then in this case, there is no variation along the x direction, but there is variation along the y direction. So if you see any one row here, then you see the patterns don't change as a function of x. But if I take any column, clearly the pattern of phases is changing. Okay. So these are some examples. So here we have the center of k-space, kx equals 0, ky equals 0. They're all in the same direction, so that's good. Here we have kx equals 0.25, ky equals 0.5. So let's see if that makes sense. So 0.25 would correspond to a spatial period of 4, and this would correspond to a spatial period of 2. So let's see if that's the case. So yeah, it does look like from here, one period from this spin to this spin, that's got a period of 4. And here, to repeat, that's a period of 2. So that makes sense. Okay. Here we've got similarly minus 0.25 and 0.5. So the question is, what's the difference there? So here, if we look at this spin here, along this row, as I go along x, this spin here has got a positive, it's negative 90 degrees. So it's going faster. So that's that kx equals 0.25. So what I'm drawing you here is e to the minus j 2 pi kx x times e to the minus j 2 pi ky y. So here, since kxx is positive along this direction, so I'm at a positive x here, then I get a negative phase when kx is positive. Okay. Whereas here, kx equals minus 0.25, and so here, let's see, am I doing this right? Minus, yeah. So minus 0.25 minus of that times, this is at 1, is equal to 0.25. So I have a positive phase in there. The period is still the same, right? The period of here is still 4, and this period is 2. And here I have still the period of 4. But you notice here, there's no variation along the y direction, so ky is equal to 0. The next thing in the Fourier transform is, we have to do that integral. And so you can imagine you're going to take your object, at every part in k-space, you're going to take your object, you're going to multiply it by the pattern. So this is your object, and this is your spatial pattern. And then you're going to integrate the whole thing, and that is going to give you your value of your object at that point in k-space. Right. So the process is take your object, multiplied by a spatial pattern, and then integrate over all space. And similarly, and then you just go to different parts in k-space, and the object stays the same, right? Assuming it's not moving. So for now, we're going to assume the object's not moving or changing with time. So you're leaving the object. The object is constant from k-space, from as you're moving along k-space. But as you're moving through k-space, you have different spatial patterns, which you use to multiply your object by. And then after you integrate, then you plug in the value and you fill in k-space bit by bit by bit. Okay, so in MRI, we're essentially filling in k-space. And then once we have enough information in k-space, we can then take the inverse Fourier transform and get back our image or an estimate of our image. So with MRI, it's nice because we can actually think about, instead of just sort of showing these pictures of these sort of patterns, we actually can think about the actual phase orientation. And so in this case, you notice here we have variation along the x direction, but no variation along the y direction. So we do multiply by that phasor pattern, or in this part along the kx axis. Similar here, there's no variation in the x direction, only variation along the y direction. So we integrate all this, we get this part in k-space. So this is an example showing you why it matters, like how the spins and the integration work together to give you the value of the k-space. So imagine you had an object, it's a uniform object, maybe like a bar of chocolate, okay, with spins in it. So the multiplication isn't really, the multiplication is just, it's not like we have a multiplier in the object, but basically wherever there's hydrogen protons, the multiplication comes by using the gradients to orient the spins such that they're have the right spatial pattern. So you notice here my object is relatively uniform, and my spatial pattern here is diagonal. Okay, so I'm taking this object and I'm imposing a uniform object and I'm imposing a diagonal pattern on it. And so essentially for every spin that's pointing like in this direction, I can find a spin pointing in an opposite direction. Okay, and so if I think about adding up all these spins, doing a vector sum of all these spins, I'm going to end up with a total spin, sort of a total sum that's relatively small, saying that this diagonal pattern isn't really a very good match for my uniform object. Now let's consider, just in this case, I've gotten, so these where there's no spins, it's like I've cut the chocolate in diagonal stripes out. Okay, so there's really no spins there. Okay, and so that's all zero. And so in this case, if I take my object g of xy times my spatial pattern, either the whatever, then at that location it's zero. So the multiplication is sort of done inherently for you, because where there's zero spin, then there's going to be zero signal. All right. And so now you can sort of see that my object, which is basically got chocolate in stripes, matches my spatial pattern fairly well. So now when I think of adding up all the spins, they add up to be a relatively large vector, all right, indicating that that spatial pattern is a relatively good match for the spatial pattern for the object. Yeah, so the question is the precession. So yeah, we would imagine in this case, you can imagine that these spatial patterns are MXY. So yeah, if you were imagining that, then the Z component would be pointing out of the paper. Okay, and everything here is in rotating frame of reference. Can you repeat why we assume those areas are 0? Basically, let's say this is my object, g of x, y. Okay, so that's a two-dimensional object. So in the first case, let's assume g, x, y is equal to 1 everywhere. So that's just a uniform object, right? So I'm just given that I have a uniform object, all right? So then I'm given some other object, let's call this h of x, y. Okay, so this is another object. And all I'm saying is h of x, y is equal to 1. Let's say it's 1 here along these. So where I have some chocolate, h of y equals 1 along, you know, so for all the air, for let's say all the areas A regions. So this is part of an A region, A, and A. Okay, and h of x, y is equal to 0 for all the B regions. So let's call this region B, B, B. Okay, so it's more just like my object, I've arbitrarily set it to equal to either 1, where I have some spins, or 0, where I have no spins. Right. So that's more just sort of, and so where I have no spins, it doesn't really, I could still think of what the spatial pattern of the spins would be if there were spins there, but because I have no spins, that contributes nothing to my overall integral because there's no spin there. So where you see these little dots, that just means I don't have anything there, and so those areas are 0, and that's because I've maybe just cut that out, so all there is air there, so there's no hydrogen protons there. Okay, so that integration is really nicely done by the coil, because the coil, this coil here basically sees everything that's in the object, and so it sees all, for every little magnetization that's spinning around, it is measured by the coil. And as long as the coil has a fairly uniform sensitivity, so it doesn't matter where the spin is, then you have this nice integration of all the magnetization within the object. Later on in a later lecture, we'll talk about what happens if the coil is not uniformly sensitive. And it turns out that actually you can consider that a problem, or you can make advantage of that and actually create new ways of doing imaging faster. So here's the recipe for doing a 2D Fourier transform. For each case space location, so this is what we're trying to do, right? We're trying to implement this equation, which is just math, right? So remarkably, MRI actually implements this mathematical equation in terms of the real world. Okay, so for each case space location, so given some kx and ky, we can create a spatially varying phasor pattern just by using the gradients. We next want to multiply the object to get gxy times that. That's just done for us by the physics, by just the fact that where there's a spin, where there's 0 spins, then gxy is just 0, so that product would just be 0. Where there's more spins, that will be more magnetization, so that will just increase. So that multiplication is just done for us. And then the integration over all of space is done for us by the RF coil receiving the magnetization from all the spins within a volume. So steps 1 and 2 can be considered the encoding steps, and then step 3 can consider the integration step, or the receiving step. And the idea is we just repeat this process over and over again by changing, every time we change the spatial pattern, we measure the integration, and that's 1 point in k space, and then we repeat that process over and over again. So this is an example of what that might look like. So this is my object here. This is the pattern. So this is the phasor pattern. And here is now this is sort of multiplying the object by the phasor pattern. So you sort of see this is basically 0 here. The black is showing where it's 0, okay? So it's 0 there, or it's 1 here, okay? So you notice where there's no object, there's no spins, right, left. And so essentially, I only have spins left over where there was an object. And here what we're going to do is, and this is sort of the sum of all those spins. And so we're going to start off at the center of K-space. And so you sort of see there's a pretty big sum. And notice as I move along K-space here, I'm changing that spatial pattern. And so here I have a diagonal spatial pattern. And so I get a very small sum because that spatial pattern of diagonals doesn't really match my object very well. Okay. And let's see where we got a big spatial pattern. So here we're actually getting fairly big vector sum, because you notice here, my spatial pattern, if you look at it, has a period that's roughly the same as the period of my object. Okay, so where that spatial pattern is matching my object, the sum of the spins actually adds up to be a fairly large value. All right. So I can, I think I have this movie, so I can put this movie also on Canvas, and you can play around with this sort of at your own leisure. Okay, so what I want to do is spend the next few minutes sort of going over through some examples, and then we're going to send you into breakout rooms to do a little exercise together. So we're going to think about some very simple things with 5x5 array of spins. And in this case, we're at kx equals 0, ky equals 0. So if we sum up all these spins, assume each one has a value of 1, then the vector sum would just be 25, assuming this is my object. Okay, my object, this is all ones everywhere. And so if I sum up 25 spins, each with an amplitude of 1, I get 25. Now here I'm at the same location in K-space. So you notice the spatial pattern here is these spatial patterns are exactly the same, right? All I've done is change my object now. So now this is a funny little object where I have ones along these diagonals, right? And then I have minus ones along these other diagonals. So I can think about here, if I sort of take each, here I've got a spin. So I can imagine where it's 1, I just have the spin pointing in that direction. So those positive spins would add up to +6, right? But now I have the spins pointing that direction, and I'm multiplying by -1, so that would flip the spins. Okay, and those add up to, what is that, -7. So my total is -1. Here I've got sort of different spatial locations. And so, for example, here I can think about looking at this here. So this here, so notice how these are all sort of, this is what's going to, only these spins will get multiplied by my object, right? So I can think about taking this spin here, and it's pointing positive, but it's multiplied by -1, so it points to the opposite direction. These spins are multiplied by -1, so they stay the same. These spins here are pointing to the right, but they're multiplied by -1, so they're going to get flipped. These spins here are going to stay negative. And this final spin here is going to get flipped. So if I look at the sum of all those spins, it's -13. Okay. I could take, what is the meaning of ones and -1s for the object? That is just a definition of gxy. Okay, so gxy can be any function. And so all I'm doing is I'm making up an arbitrary function that has ones and -1s or zeros. So in general, you can make up any object, but and in general, in real life, you're not going to have necessarily objects with ones and -1s unless we talk about the phase. But for now, these are just sort of made up objects. Okay.
Oh, so it's just like the magnitude of the magnetization, or it's the like the T1 or T2. I mean, for the G.
Yeah, so that's a great question. So yeah, this is probably the ones with -1s would mean that at that point, for some reason, the phase would be flipped by -1. So you might, later on, we might show that you can get that by having something flowing in a certain direction with a certain pulse sequence. But for now, just think of it as sort of a theoretical object. These are not, the ones with -1s for now, don't think of it as a real object. It's just sort of some imaginary object. So don't worry about that for now. Yeah, it's just to sort of get through, the math of this for now. Okay, so then this is a more sort of, obviously solely positive objects are a little more realistic, and so it's only ones or zeros. And so you notice the spatial pattern here is such that we've got it is also diagonal variation. So we have here, things are the same along the diagonals, right? So everywhere, if you look at any diagonal, it has the same orientation of spins. And so here, what we can just do is we can grab those spins. And so it turns out that these are positive. They're all positive. The spins that we pick up are all pointing in that direction. Okay, so that has a vector sum of 13. All right. And this movie here, let's see, what is it showing? Yeah, I think this is just showing different spatial patterns and then assuming a uniform object. And so we're showing that the K-space is largest here, where we're at the center of K-space, and anywhere we go off in K-space, all other K-space patterns give you a very small value for the Fourier transform, because for a uniform object, the best match is when all the spins are pointing in the same direction. Now here we have an object where, like the one we just did, where all these spins here are missing, right? Okay. So if I have a uniform object, so basically, if I have uniform spatial pattern, there's still, things are still going to add up, but I'm also going to find out that there's going to be, oops, how do I get this working? As I change that spatial pattern, there should also be, let's see. There should also be a pattern where it matches better. Let's see. Is that not working? Okay, I'm gonna have to figure out what's wrong with this, but let's move on to the exercise. So we have about 12 minutes. So what we're gonna do is we're going to, I'm gonna explain what to do. So first of all, can everyone maybe log into this website? I'm gonna activate this. Can everyone see, if you go to this website, can everyone? Can people see this website? Okay, great. So what we're gonna do is I'm gonna explain what the exercise is, and essentially, this is your object here. So it's a very simple 3x3 object. So you have ones where it's orange and zeros everywhere else. Okay. And then the blue arrows here are representing the spatial pattern of the spins. Okay, so those are the spatial patterns, and you notice there's an arrow for every location, even though the spin may not exist at the location, showing which way the spin would be oriented if there was a spin there. All right. So let's do the first example together. So for each one, we're trying to say the answer is, and you should only answer once per group once you're in your breakout room. So you can wait till you're in breakout rooms to answer. You're going to put the names of the people in your group, whatever group it is. And then you are going to put in what's the vector sum after multiply and where in K space you are. Okay, so let's do A together. So you're only going to be responsible for B, C, D, and E. All right. So let's say A. So in A, you notice all the spins are pointing in the same direction, right? So what would Kx equal here? We would have Kx equals 0 and Ky equals 0. Okay. And the vector sum would be 1, 2, 3, 4, 5, would just be 5. Okay. So your job is to put in the values for B, C, D, and E. So what is the vector sum of the multiplication of the object and the spins? And where are you in K-space? Or what's your best estimate of where you are in K-space? Okay, so are there any questions before we send you into breakout rooms? Let's see, how do I do that? Breakout rooms. So I'm going to have 9 breakout rooms, so there should be about 2 to 3 participants per room. If you have any questions, just let me know. And try to, when you answer the questions, just put them all in one row. So it's like A, B, C. And so it'll be easier for me to look at. All right. Any questions before we go? Okay. All right, here we go.
Hey, Tom.
Hey, just checking to see if you have any questions.
Yeah, what are the values for the up and down arrows?
So that'd be like plus J or minus J.
Oh, okay.
Yeah.
Okay. Oh, great. That makes things super easy. All right.
Okay. All right. Any other thing? Anything else?
I think that's it.
Okay, I'll go to another room. Okay, bye.
Thanks, Tom.
Sure. Do you guys have any questions?
I don't think so. I mean, I'm going to assume these vertical arrows are half.
They're plus J or minus J.
Yes.
Okay, great. Okay, I'll take off and go visit another room then.
All right.
Thanks. I just wanted to see if you had any questions.
Oh,
Yeah.
yes, we do.
So
Thank you.
we think that the sum is -5.
For which
B.
one?
For B.
For B. That would be, well, you have one arrow pointing 1. So you have a 1, and then you have 4 negatives, right? So what would that be? So
So it's
1 minus 4 is what?
-3.
3.
Yeah.
Oh, because we saw there was another example where it's like -13, even though they weren't all, like if you added them up.
Yeah. Well, that's because the ones where you have to think about, in that case, the negative ones are being flipped. So all the things along the diagonals all add up, right? So there's 13 non-zero things there.
Right. So
Yeah.
then if you add the +6 and the -7, then it's like -1. But then I was right.
Well,
Yeah.
because you have the negative ones, but then the where you have negative ones, the arrows are pointing in opposite directions. So when you take the phase and you negate, you can't see my hand. You have the phase, let's say you have the phase here, and then it's negated. It multiplies by -1, so then it points in the -1 direction. So if you look in the top left-hand corner, you have a -1, but its phasor is pointing in the positive direction. But once it gets multiplied by -1, it points negative. So all the things are going to point negative. Whereas in this case, you only have ones, right, in your object, so nothing gets flipped, right?
I see.
So 1 times an arrow pointing in this direction leaves the phasor pointing in the same direction.
Okay.
Does that help?
Yeah.
Okay, good. If there's no more questions, I'll go to another room.
We're actually also confused about the
Yeah.
case-based thing.
Yeah.
How to approach it. And so is this one just 0 because they're all like neutral and it hasn't started moving?
Yeah, A is 0 because it's more, they're all, to look at where you are in k-space, you just have to look at the spatial pattern of the spins. And so in this case, they are all pointing in the same direction, right? So there's no variation. Whereas in B, is there any variation along the rows?
So the
Yeah.
rows are variation, but the y is not. So it's ky equals 0 and then kx equals?
1 over its spatial period. So what's the spatial period there?
2.
Yeah.
So 1/2, 0.5?
Yeah.
Okay, gotcha.
Yeah.
Cool. Thank you.
Okay,
That
sure.
makes sense.
Yeah.
Thank
All
you.
right. See you later. Okay, so we're waiting for people to come back from breakout. So we'll go through, we'll just go a few minutes past just to finish up this just to go over the this problem. If you need to leave early, it is we are recording, so you can always catch up on that later if you need to. Okay, so I think most people are back from the breakout rooms. So let's go through this. Can everyone hear me and see the screen? Yeah, great. Okay, so let's look at B first. So B is, so one thing is the object is 1, and so it's 1 where there's something and 0 everywhere else. So we're not going to have any flipping of the spins or anything. So we can just do a straight vector sum of all the spins that are there. So for B, if we look at the spins, we have 1 that's pointing there, so that's a +1, and then all the other spins, this one, and this one, are all pointing in the opposite direction, so that's -4. So there, the sum would be 3. Okay. Now where we are in K space is, if I look at a row, there is variation across the row, and it has a period of 2. Okay, so I would say kx equals 1/2, and we can't really tell the sign because we don't know which, how it got there. And then if I look at any row, there's any column, sorry, there's no variation along the column, so ky would be 0. All right, so that's B. Let's look at C. C is, we've got, once again, +1 and -4. So that's also -3 as the sum. But here you notice that there's no variation along the rows, so kx equals 0. There is variation along a column and has a period of 2, so ky would equal 1/2. Right. This one here, they're all pointing in the same direction, right? So that sum is equal to 5. And here I have spatial variation this way, right? So that's kx equals 1/2. And we also have spatial variation in the y direction. So also ky is equal to 1/2. And so that sort of makes sense. This is sort of a diagonal pattern of the spins. My object is somewhat diagonal. And so the fact that I have a larger sum makes sense, right? And the last one is, this is a 1, right? And then I have, this is plus j and minus j, but all those cancel out. So the sum is just 1 at the end, right? And then where am I in K space? Well, here, there's definitely a kx variation. And in kx, the period, if this is half a period is 2, so total period would be 4. So I'd be at kx equals 1/4. Okay. And since the spin from here to here had a clockwise rotation, then I know I'm at kx equals 1/4. And then here, there's no variation in the y direction, so I know ky is equal to 0. Right? So that is what we're going to do for today. And so let me bring up a chat. Okay, hold on just a minute. B should be -3. Okay, yes, thank you for pointing that out. -3. Yeah, 1 minus 4 is -3. All right, are there any questions before we end? Okay, so if there are questions, you can always, can you explain again kx for E? Okay, for E, you notice here, this is pointing up and this is pointing down, right? So that's half a period, right? Something pointing one direction, another direction. To do that, that's half a period, and that distance for half a period, it's 2. So we know a full period has a period of 4 if we wanted to go all the way back, such that up is up again. All right. So that means that if the period is 4, then kx would be equal to 1/4. Does that help with that question? Okay. So let me just go over a little bit of logistics. So there is no class this Wednesday because it's Veterans Day. So the homework is due on Thursday. And then next week is project presentations. And so Professor McVeigh will be sending out some email about sort of scheduling of that. And then, so it's not going to be, we're going to sort of miss 3 classes. There'll be, there's going to be 3 class sessions, or we'll miss 1 class session, and we'll do 2 class sessions of project presentation. So it's not going to be from 2 weeks from today that we actually have the next MRI lecture. So what I'm going to do is either probably Wednesday or Thursday, I will post a 2-week problem assignment for everyone that will use material from these first 2 lectures and maybe 1 supplementary video. So it will be slightly longer than a normal homework assignment, but not too much. And so I would just say, it'd be good to start, maybe start working on it now while things are fresh, but then you sort of still have time, from 2 weeks from now to work on it. So that's sort of the overall logistics that we're talking about, since the schedule is a little bit funny this year. All right. So any questions? Okay, clockwise is positive, clockwise is negative. Okay, let me just explain a little bit about that. So what I said was that there is, because we're defining things as e to the minus j 2 pi kxx, okay? So clockwise rotation is negative. And in this case, if I go from, say, here to here, okay, as a function of x, then if kx is positive and x is positive, then I will have a negative phase, and so that's the clockwise rotation. Right. So yeah, so the bottom line is, anytime you're dealing with phasors, and it can be a little bit confusing, and so the good thing is, it's really good to really think about, always go back to the definition. Let me see what's on the next slide. There's no space there. Okay, let me write it here. Always go back to the definition e to j theta. Okay, that's always a safe place to go. So you're always going to look at, what's this argument theta, right? And then theta, theta here is defined as positive, and this is defined as negative theta. Right? So if there's any question about where theta is, just look at what is the argument of e to the j theta. Okay, so in the case of e to the j 2 pi kxx, you're just looking at, what does 2 pi kxx look like? Is it positive or negative? And so we know that if x is greater than 0, this is the term e to the minus j2. So we know that the theta in this case is theta equals minus 2 pi kxx, because I have that minus term. So if x is greater than 0 and kx is greater than 0, we know that for all kxx in that regime, theta is going to be negative, because kx and x are both positive, right? Okay, so I can stick around if there's questions on the homework, or if people have questions on the project, Professor McVeigh's online, and so we can sort of do both. So I will stay around for office hours until people, as long as people have questions.
Professor?
Yes.
I have a question about the homework number 2.
Okay.
So the convolution part is that, so in the sine function, there's a 10 times u. Like there's like so how do we define convolutions for like that's like it's a 10 times u something?
Can you remind me what the question is again?
So it's basically the Fourier transformation. It's like I can share the screen. Like, I mean, it's
or
the
just tell me and I'll write it down.
Okay,
Tell me what it.
It's sine x over 10 convolute cosine 2 pi times x. Yeah, and you want to find the Fourier transformation for this.
Okay, so you want to take the Fourier transform of that. Okay, so great. So what is
your
question?
Sorry, it's the other one. It's the other one. It's there's no convolution for this one. It's the multiply. Yeah.
Okay. So you want to multiply these two together.
Yeah, so you get a convolution in the Fourier space.
Right, so you can take the Fourier transform of this and the Fourier transform of this, and you're going to convolve, right?
Yeah.
Okay, great. So that's good. So what is your what's the question you'd like to ask?
So because when you take the Fourier transformation of the sinic function, you get 10 sinic 10 times. Oh no, it's the rec. It's the rec 10 times u, right? No, rec, yeah, 10 times. Yeah, something like that. Yeah. So there's like a 10 times kx. I don't know how to convolute like with, because the definition of the convolution is like for only for like kx only. I don't know how to do when you have a 10 in the front.
Okay, well, first of all, what does that function look like? A rect of 10kx. How would you draw that? So that's just a function, that's a function of kx, right?
Yeah.
Okay, so first of all, what is the range of that function? Where is it non-zero? From kx equals what to what?
To 5. No, it's a 1 over 2, right? Something.
Yeah, so remember the rect function, right? Let's say rect of anything, right? Is only it's only going to be non-zero when its argument is less than 1/2, right?
Yeah.
Okay, so we can say when is 10kx equal to 1/2? Kx equals what?
5.
Well, what if I divide both sides by 10?
Oh yeah, no. Yeah, 1 over 20. Sorry.
1 over 20, right? So basically, this means that I'm going to have 1 over 20 and minus 1 over 20, right? And it has a value of 10, right?
Yeah.
Okay, so that's my rect function. Now, what is going to be the Fourier transform of sine 2 pi x?
It's just delta kx minus 1.
Okay, is it just a delta, or does it have other, like the sine? Like if you write a sine.
Oh, 1. Yeah. You're right. Yeah, it's 1 over 2 times the whole thing, like delta kx minus 1 plus delta kx plus 1.
Right.
Something
So
like
you'll
that, yeah.
need to check on that. But you remember that you can always take sine of x or sine of anything is equal to e to the jx minus e to the minus jx, right, over 2j, right?
Mhm.
So you want to make use of that. But let's just sort of work through. I'm not going to go through the exact equation, but so you have, this is going to have two delta functions, right?
Yeah.
Oops, let me get rid of that. Okay, so this Fourier transform here, right, there's going to be a delta function. Let's say there's two delta functions, right? Let's say there's a delta function here and there's another delta function here. It's minus, right?
Mm-hmm.
And there'll be j terms around. I'm going to drop the j terms for now, but in your homework you'll need to have that. So where is this? What's the frequency of this delta function? Where is it located? How far away? Yeah, where's that frequency?
It's 1 and minus 1, I think.
Yes, 1 and minus 1. Okay, so that's good, right? Because sine 2 pi x, right, is equal to 2 pi kxx, where this is just equal to 1, right?
Mhm.
So that's good. So we basically, now you have this thing here, and you have to convolve it with two Dirac delta functions, right?
Yeah.
Okay, so this is where you want to use this thing where if I have any function g of x, and then convolve it with delta x minus x naught, it just shifts my function.
Oh, I see. Okay, okay, I see.
Yeah. So that's something where you want to
see.
just make use of that fact.
Okay, so you take the new function, the rect function. Okay, I see. Yeah, that makes sense. Yeah. Thank you.
Sure. Okay. Any other questions?
Also for like problem 3.
Yep.
So it's the integration of the sinic function.
Mm-hmm.
So are we supposed to derive it or just like check it online for the integration value?
You're supposed to use, well, so basically, part A, right? In part A, so this is 3A, right?
Yeah.
Let me just explain. So this just tells you that you want to prove that this is true, right?
Yeah.
So what is this? If f of t is my function, what does this integral represent?
It's just, well, it's a summation of over the whole space.
Right, which is called the area, right?
Yeah. Yeah.
Okay.
Oh, okay.
Right. So we know that we can get the area of the function by just taking the Fourier transform and evaluating it at 0.
Right. Oh, I see. Okay.
Right. So that should help. Yes.
Oh.
Go ahead.
Oh, so you mean I should take the Fourier transformation of the. Okay, I see.
Yeah.
Right.
And the Fourier, the Fourier transform of the sinc function, right?
Right. Right.
Yeah.
Yeah. Oh, okay. Yeah, that makes sense. Yeah.
Yeah. Sure. Are there any other questions? Okay, I'll stay on for another few minutes. So if you have any questions, please let me know. And otherwise, we'll sort of end the session in another minute or so.
Hey, Tom, I just want to reiterate that I am also online now if anyone wants to speak up with a question about the projects or something.
Okay, great. Yeah, so let's open up to project questions then, if anyone has those.
Professor Elliott,
Yeah.
so since we refocused our topic